A healthy forest maintains a careful, quiet balance, but it only takes a single lightning strike or one stray spark to ignite a chain reaction. A glowing ember meets a dry leaf, catches a breath of air, and bursts into flames. From that initial ignition, the escalation is violently fast. A tiny ground fire can race through dry grass in a matter of minutes. Given the right conditions, those scattered flames will climb into the trees, turning thousands of hectares of timber into an ocean of fire within hours. The sheer energy released by a large fire can actually dictate the local atmosphere. Look at these massive white columns. Those are pyrocumulonimbus clouds, formed when extreme heat forces moisture and smoke high into the sky. The fire is literally creating its own weather system, capable of producing dry lightning and fierce winds that spread the blaze even further. This transition from a microscopic chemical reaction to a regional atmospheric event follows a specific scientific sequence. To see how a single spark scales into a landscape-altering disaster, we have to look closely at the mechanics of the burn. The scale of modern wildfires is difficult to comprehend. During the 2019 to 2020 Australian Black Summer captured here, fires burned through more than 24 million hectares of land. An estimated 3 billion animals were either killed or displaced by the flames. The threat extends directly into human communities. In 2018, a faulty electrical transmission line ignited dry vegetation in California. The resulting campfire swept through the wildland, completely leveling the town of Paradise and leaving dozens dead amid the wreckage of their homes. Even if the flames never reach your town, the effects can cross borders. In 2023, record-breaking fires across Canada generated dense smoke plumes that drifted hundreds of miles south, triggering severe air quality alerts across the North American continent. Wildfires are no longer isolated local events. They disrupt international supply chains, drain emergency economies, and require an urgent, unified scientific response to manage. To manage a fire, you have to break it down to its chemistry. This diagram shows the traditional fire triangle. A flame requires 3 basic ingredients to survive: heat to start the ignition, fuel to burn, and oxygen to sustain it. Remove any one of these 3, and the fire dies. But modern fire science adds a 4th dimension to this model, creating the fire tetrahedron. To keep a blaze raging, the heat must continually vaporize the fuel, mixing it with oxygen to create a self-sustaining chemical chain reaction. Breaking this specific reaction is exactly how chemical fire retardants work. Once a fire establishes that chain reaction, the local weather takes the wheel. Prolonged droughts dry out the vegetation, high temperatures preheat the environment, and strong winds push the flames forward while supplying a continuous rush of oxygen. The shape of the land also dictates the speed of the spread. Fire naturally moves much faster uphill, accelerating through narrow valleys and along steep mountain slopes. This uphill acceleration happens because of radiant heat. As you can see in this cross-section, the immense heat from the fire rises. It hits the untouched green vegetation above, bakes the moisture out, and turns it brown and dry. The fuel is prepared for ignition before the actual flames even touch it. A catastrophic blaze is the result of chemistry, weather, and topography perfectly aligning. Fire behaves differently depending on what layer of the forest it consumes. This is a surface fire. It's the most common type, burning through dry grass, fallen leaves, and low shrubs, keeping the large, mature trees intact. But if those flames catch dead branches and climb into the canopy, they become a crown fire. Crown fires spread rapidly from treetop to treetop. Riding the upper winds, they are incredibly dangerous and nearly impossible for ground crews to stop directly. Then there are ground fires, which burn beneath the surface. They consume deep layers of peat and organic soil. These fires can smolder underground, out of sight for weeks or even months, only to resurface when conditions dry out again. You can see the impact of dry conditions and steep topography here in Uttarakhand, India. During intense heat waves, long lines of fire sweep across the region, following the steep ridges. These recurring events burn away vital forest habitats and blanket local communities in dense smoke. Despite the visible destruction, many of these environments depend on the heat of the burn. Some forests evolved alongside periodic fire, using the flames to clear out dead underbrush and return trapped nutrients to the soil. For certain pine species, a wildfire is actually the only way to survive. Extreme heat melts the resin on their cones, allowing seeds to germinate. Eliminating fire entirely would eventually choke the forest. The challenge for modern society is managing the balance between ecological health and human safety. When a fire threatens populations, we rely on brute force engineering to slow it down. Specialized aircraft drop thousands of gallons of water and chemical suppressants to cool the canopy, while bulldozers scrape massive clearings in the dirt, called fire breaks, to physically remove the fuel in the fire's path. Paradoxically, one of the best defenses is starting fires ourselves. In this controlled burn, land managers carefully set fire to dead leaves and dense scrub under strict weather conditions. By consuming the fuel now, they starve any future uncontrolled wildfires that might sweep through the area. This preparation is vital at the wildland-urban interface, the exact point where human development meets the forest. For homes in these zones, survival requires creating a defensible space, removing dry vegetation near structures, using non-combustible roofing, and having a strict evacuation plan before the smoke ever appears. And the smoke is a severe threat on its own. As this firefighter's heavy respirator makes clear, you do not need to touch the flames to suffer the consequences. Wildfire smoke is thick with hazardous aerosols that travel thousands of kilometers, causing respiratory illness far outside the burn zone. Surviving a severe fire season demands constant land management, resilient engineering, and the discipline to evacuate immediately when the warning comes. While scientists cannot predict exactly when or where a stray spark will land, they can calculate exactly where a forest is most vulnerable. We are now shifting from reactive firefighting to predictive disaster management. By combining real-time satellite data with artificial intelligence, systems can scan vast topographical maps to visualize moisture levels in the soil and vegetation. These fire danger indices allow agencies to pre-position crews in the most dangerous, dried-out zones days before a heat wave even hits. The manual watchtowers of the past are being replaced by smart forests. Networks of ground-based environmental sensors monitor the microclimate, while autonomous drones equipped with thermal cameras map out hidden hotspots through thick smoke. On the ground, new homes are being constructed with ember-resistant vents and specialized materials designed to withstand extreme radiant heat without igniting. Wildfires will continue to burn. The raw chemistry of fuel, heat, and oxygen guarantees it. But by studying the science of the spread and deploying next-generation technology, we can learn to safely coexist with the flames.